If you follow renewable energy even a little bit, you already know that perovskite solar cells have taken the photovoltaic world by absolute storm. I mean, they're delivering these incredibly rapid efficiency gains that are literally shaking up the whole industry. But today, we aren't just talking about the material itself. Nope, we're zooming way in to look at the specific layering of these cells, because it's this precise, microscopic engineering that's the silent engine driving this massive revolution in solar power. And we're going to break it down for you, literally layer by layer.
Now, to really grasp how these cells do what they do, we have to understand what we call device architecture. So what is that? Well, device architecture is simply the specific spatial sequence, the exact layering of semiconductor junctions relative to the glass base, which we usually call the substrate. Think of it like a master blueprint. It dictates exactly how these microscopic solar sandwiches are physically ordered, which creates the energy gradients needed to actually capture sunlight and convert it into usable electricity. If you tweak that blueprint, you completely change how the entire cell performs. So here's our roadmap for today. First, we'll look at the anatomy of a solar sandwich, then we'll break down the complete layer stack. After that, we'll explore their origins and two different legacies, compare regular versus inverted architectures, weigh the pros and cons of each, and finally take a peek at the future of solar tech.
All right, let's kick things off with Section 1, the anatomy of a solar sandwich.
I absolutely love using the sandwich metaphor to describe the cross-sectional geometry of these devices. But to truly appreciate this particular sandwich, you kind of have to warp your sense of scale. When we stack all of our active ingredients together, meaning the entire functional working parts of the cell, that total active stack is roughly 1/100th the thickness of a single strand of human hair. Let that sink in. It's an almost unimaginable feat of nanoscale engineering.
To put a hard number on it for perspective, if you exclude the 1 to 2 millimeter thick base glass, which just provides structural rigidity and doesn't actually play a dynamic role in the physics, this entire 5-layer powerhouse is usually less than 1 single micrometer thick, less than a micrometer. We are literally managing light and electricity across multiple distinct materials in a space smaller than a single bacterium. It's just wild.
Moving right along to Section 2, the complete layer stack. Let's build this thing from the bottom up.
So, let's actually build this incredibly thin device layer by layer, starting from the glass that faces the sun. First up, sitting right on the glass, we have Step 1, our transparent conducting oxide, or TCO. Step 2, we lay down a bottom transport layer. Step 3 is the absolute core of the whole device, the perovskite absorber itself. Step 4 wraps that core in a top transport layer. And finally, Step 5, we cap the entire thing off with a top electrode. And there you have it. That's our spatial sequence.
The crucial part here is understanding what these specific materials actually do inside the sandwich. The TCO, the transparent conducting oxide, often materials like FTO, which is fluorine-doped tin oxide, acts as the front window. It has to be highly transparent to let the light in, but conductive enough to pull the electricity out. Next, we hit our transport layers, which basically act as highly selective bouncers at a club. The electron transport layer, or ETL, using materials like tin oxide or PCBM, lets negative electrons pass right through, but strictly blocks positively charged holes. Right in the middle is the perovskite. This is the heart of the cell. It has a crystal structure mimicking calcium titanate, and when sunlight hits it, it creates electron hole pairs that split apart. And just to clarify, holes are really just positively charged voids left behind when that sunlight knocks an electron loose. On the other side, we have the hole transport layer, or HTL, using materials like spirometad or nickel oxide. This is our opposite bouncer. It extracts those positively charged holes and blocks the electrons. Finally, the top contact, usually a highly conductive metal like gold or silver, closes the circuit. Unlike that transparent bottom window, this back metal layer acts as a solid, opaque electrical terminal.
Okay, so how did we figure all this out? Let's get into Section 3, origins and two different legacies. If we look back at the timeline, perovskites were actually first used in solar cells around 2009, but back then they were just tiny sensitizing dyes floating in liquid systems. It wasn't until researchers realized perovskites can transport electricity as solid layers that a major historical split happened. Scientists who are already working on dye-sensitized solar cells basically just dropped perovskite into their existing structures. That naturally created what we call an NIP flow. Meanwhile, a totally different group of researchers coming from the organic photovoltaic and OLED display world were used to working in reverse. So they swapped out their plastics for perovskite, creating the exact opposite, a PIN flow. Essentially, this one massive breakthrough forced two different scientific factions to build two competing structures.
Which brings us perfectly to Section 4, regular versus inverted architectures.
Now, this naming convention simply comes from the order of the layers. N stands for negative, or electron selective. P stands for positive, or hole selective. And that I in the middle, that's the intrinsic Perovskite center. The whole difference between a regular NIP and an inverted PIN is decided purely by which transport layer the incoming light hits immediately after passing through the front glass. It's really that simple. In a regular NIP cell, sunlight hits the electron-selective side first. In an inverted PIN cell, the structure is completely flipped, so sunlight hits the hole-selective side first.
And because those layers are flipped, the physical behavior of the cell under the hood fundamentally reverses. In an NIP cell, electrons are pulled forward toward the illuminated glass side, while the holes travel away toward the dark back metal contact. But in a PIN cell, that physical pathway is totally reversed. The holes are the ones pulled forward towards the glass, and the electrons travel to the back. Think of it like a complete change in the direction of traffic flow.
And it gets even more interesting if you look at them under an electron microscope, because their microstructures are completely different too. Traditional NEP relies on a mesoporous scaffold. Imagine a rough, highly irregular sponge network of nanoparticles. The catch here is that it requires extreme baking. We're talking around 500 degrees Celsius. On the flip side, sign pen cells are almost exclusively planar. They look like incredibly neat, flat geological strata sitting as smooth, distinct sheets. And the best part? They can be processed at super low temperatures, often well under 150 degrees.
So, which one is better? Let's dive into Section 5, weighing the pros and cons.
Choosing between these two designs is really a tightrope walk between maximum power, manufacturing costs, and long-term stability. Let's look at the regular NIP architecture first. It gives us the absolute highest peak efficiencies and uses thick, robust absorbers. But it suffers from severe hysteresis and, like we mentioned, requires massive amounts of 500-degree heat to manufacture. Hysteresis is a huge problem. It leads to unpredictable power output readings and can literally physically degrade the cell over time. Inverted PIN, on the other hand, is completely hysteresis-free. That means incredibly stable power output, plus its low-temp printing makes it absolutely perfect for cheap, flexible plastics. The trade-off? Well, historically it's had slightly lower voltage and very delicate top contacts. Because those pin structures are so smooth and thin, applying that final heavy metal layer on top without accidentally damaging the delicate layers underneath is notoriously difficult.
All right, finally, let's wrap up with Section 6, the future of solar tech. To really grasp the cutting edge of where this is all heading, we have to look at a massive recent shift in those inverted PIN structures. The real game changer here is the introduction of self-assembled monolayers, or SAMs. Scientists are essentially replacing bulky polymer layers with these SAMs, which are literally, and I mean exactly, one molecule thick. One molecule! They anchor themselves perfectly to the glass, use almost zero material, and this brilliant innovation has pushed PIN cell efficiencies right up to the heels of the top-performing NIP structures. It is absolutely incredible. And that leads us to this incredibly powerful takeaway from the field. While NIP won the initial sprint for the highest efficiency, PIN is winning the marathon for commercialization. Now, why is that? It's because the future of the entire solar industry relies on what we call tandem cells. This means stacking perovskite directly on top of traditional, commercial silicon cells to capture way more of the sun's spectrum. Here's the kicker. You simply cannot bake a silicon cell at 500 degrees Celsius without totally destroying it. So that makes the low-temperature inverted PIN design the only truly viable option for modern manufacturing lines.
So I'll leave you with this final thought. We've seen how a device structure less than 1 micrometer thick can dictate the entire future of energy. With these microscopic, low-temperature PIN sandwiches now ready to be stacked right onto existing silicon or even printed continuously onto flexible plastics, like printing a newspaper, will perovskite cells soon coat every surface in our cities? The nanoscale engineering is already there. Now we just get to watch it change the world. Thanks so much for joining me on this explainer, and keep learning.